So we're on our last topic in wave optics, which is polarization, which, to be honest, could have been our first topic in wave optics, polarization, because this has to do with the fundamental characteristic of light. So remember, light is an electromagnetic wave, and that means that light has an electric component and a magnetic component. And what's happening, again, is they're just like bootstrapping each other through space. And we never talked about this, but the electric field points in some direction, up, down in this case, and the magnetic field points in some direction, left, right in the case that I tried to draw. This is what's called the polarization of the electromagnetic field or wave. And specifically, the polarization is the direction. It's really the axis of the E field. So this isn't physics, this is like manners in some sense. We just picked the electric field to call the polarization. So in this case, we would say the polarization of this electric field, or this electromagnetic wave, is up-down, because that's the way the E field's pointing. And in this case, the electric field would be this kind of like left-right, what I was trying to draw as into and out of the board. So this would be the polarization. And this is a bit of notation of this electromagnetic wave and that electromagnetic wave. So it turns out that we kind of didn't really worry about this for the most part, because the sun, being a very chaotic entity, is actually making all of these in equal measure. So we'll have a little bit more notation where we'll describe perfectly polarized light in that way. By just drawing with, so this is an axial vector. Doesn't have a direction. It's going up, down, up, down, up, down. So it's got two heads on it. Unpolarized light. And this is what you get from the sun or a light bulb or something like that. Again, something that makes light by just banging atoms into each other. It's got no preferred direction. It's actually really hard to make perfectly polarized light from the get-go. What you have to do is take this and then polarize it, which is what we're about to do. And these kind of bristly vectors that tell you the orientations of the electric fields, what we'll do is we'll just stick this extra feature on top of our ray diagrams, because all of a sudden it's going to be important. So for instance, light from the sun, I would draw that. So here's the ray, and we're used to seeing that ray, the ray coming off of the sun. And to indicate that the sun is producing unpolarized light, I would draw that, right? And maybe I'll draw a couple of them. So again, this is just notation. You think about it like the way that you think about drawing a resistor diagram in circuits or an inductor or something like that. This is just to indicate that I have unpolarized light. Okay, so what can I do with unpolarized light? Well, I can polarize it, and there are reasons to do that, and there are natural and unnatural ways of doing that. But first, let me show you what I mean, because we have some kind of nice polarizers. So there is a lamp. Let me zoom in a bit. Let me kill some lights. And the lamp has one polarizer in front of it. So it turns out that like what a polarizer is doing in some sense is it just has a whole bunch of, in this case, oriented bits of plastic, so electrons can go in this direction, for instance. And if you try to wiggle them, they'll kill your electric field. So basically what a polarizer does is it kills all the electric field in one particular direction. So I've got some light, and I polarize it, and you don't notice any difference, right? So that would be going from the bristly full polarization diagram to an unbristly polarized one. So the fun happens when I have a second polarizer. So here's a second polarizer, and I'll put it there. Let me go and make sure this is doing what I want it to do. And you also should notice that there's not a tremendous amount of difference. So I had some light, I polarized it, and then I polarized it again. Turns out what I did is I polarized it in the exact same direction. So these are both maybe up-down polarizers. So here's the fun part. Let me turn this polarizer by 90 degrees. and it happens pretty abruptly. So now what do you see coming out of the lamp? So the first polarizer killed the up-down polarization, for instance, and the second polarizer by turning it 90 degrees. So first I killed all this stuff, then I killed all that stuff, which means I killed everything. Right? And I'll just rotate it a little bit back and forth so you can see how abruptly that happens. Almost like a cosine squared, one might say. Okay. So again, there are reasons to do this, and you might get naturally polarized light. So what this is called is, or dictated by, the so-called law of Malus. And I'll write that up, and then we'll use it a little bit. And then I'll show you guys a bunch of applications of polarization, mostly because they're pretty cool. Okay. So the next icon we have is a polarizer. And call a polarizer, or an ideal polarizer. We'll denote it like this. It turns out that if you learn a fair amount of E&M, you realize that the actual electrons are free to move in the opposite direction. But this icon is chosen in such a way that it kind of makes you think about, if you were in prison and there were bars on the door and you wanted to pass a note or something like that, you couldn't pass the note that way, you would have to pass the note that way. So this is the light that comes through. So again, these are all icons. These don't really mean anything. And now what we can do with our sunlight is we can polarize it and then polarize it again. So sun produces totally unpolarized light. And now what I can do is I can put a polarizer in front of it, and we'll just polarize it in this direction. So the thing that would come out is light polarized parallel to this direction, so the so-called axis of polarization. And then what I could do is do just as we did in that demo. I could put a second polarizer here, perpendicular to the first one, and this one is going to kill all the light that is not traveling in this direction, but all the lights traveling are polarized in that direction, so we would get no light. Okay. So this is a topic that we didn't dig too much into detail about, but the way that you talk about light, casually speaking, the brightness of light is its so-called intensity. And if you asked about the intensity, and we started with some initial intensity, we could ask the following questions. What's the intensity after it passes through the first filter, and then what's the intensity after it passes through the second filter? That's 0. And this would be measured in watts per meter squared. Just that's the units of intensity. And another question is, what might happen if we actually turn this not at a 90-degree angle, at some more complicated angle? So we're going to have like two bits of information. So first, realize that I naught. So only half of the light is going to be canceled off. So it turns out, it's a little bit more subtle than that. But if I pass unpolarized light through a polarizer in any direction whatsoever, what I'm going to get here is half the initial intensity. So I1 equals I naught. And that's actually a true statement in general, is that the intensity of polarized light, so pass it through one polarizer, and it's got to be an ideal polarizer, is 1/2 the initial intensity, right? So basically we killed everything in one direction. So now I have polarized light, and I can ask what the difference is if I pass it through a second polarizer. So a second polarizer is given by the so-called law of Malus. And this is no light because we said 90 degrees, but if it were at some arbitrary angle, this would be the relationship. I2 equals I1 cosine squared of theta. We're just making sure that I'm using the same notation as your book, which is good, where theta is the angle in between the polarizer and the polarization axis. So the angle in between the polarizer, so let's take a polarizer and put it at some angle. And we've got polarized light coming in. So this is what we do with unpolarized light going through polarizer. This is what we do with polarized light going through polarizer. So here's polarized light going through a polarizer, and this is the angle we care about. So this would be the angle of the light itself before it passes in, and this would be the angle that the polarization axis is set along. Right, so that's the theta. So I could tilt these both together. The only thing that this is saying, what this is saying is the only thing that's important is the relative angle in between the light and the polarizer. And the cosine squared is the kind of sneaky thing that makes this a little bit magical with the 1/2. Okay. So let's just do a quick, kind of sad to erase my beautiful drawings, but let's do a couple of examples. And then we'll do weird polarizer stuff. And a lot of it will be cultural, because some polarizer phenomena are actually like pretty counterintuitive, I guess you would say. So let's say that I have, we'll just set up this situation because it does everything. So let's say I have two polarizers that are offset by 60 degrees. And essentially, I want to do this. I've got light, and then I've got these two things, and I'm going to offset them by 60 degrees. Actually, you guys can see that too. So I should disappear, right? I don't know. We'll see. See how it comes out. OK. So light. Polarizer 1. And again, it doesn't matter what the actual angle is. The only thing that matters is the relative orientation. So the relative orientation in between these two polarizers is 60 degrees. So this is up, down, and this is left, right, and the angle in between them, really drawing that giant, is 60 degrees. Trust my number, not my picture. Okay. So what happens with this light that's coming out of this thing? So I would maybe stop and try to do this, in fact. So pause. So got light. I'll add the bristly icon to my ray to indicate this is unpolarized light. It's coming from a chaotic source like the sun. Passes through this. I get polarized light, and it passes through this. So this is important. I'm going to lose some intensity, and I'm going to end up with light that's polarized in the same direction. So what we have from the law of Malus is just how much intensity goes out. And the thing that I didn't say as clearly as I could have is that just like this only let in the light that's parallel to its polarization axis, this only lets through the light that's parallel to its polarization axis. So this would rotate the polarization, if that wasn't obvious just from the fact that they do the same thing. So in pictures, this is how this would look. In numbers, let's call this I0, let's call this I1, and let's call this I2. So I0 is I0. That's what the light gives us. The action of a polarizer on unpolarized light is to kill half. So I1 is 1/2 I0. And then law of Malus tells us how to get from I2 to I1. So cosine squared 60 degrees. Of course, I'm remembering that my calculator is in degrees. I feel like I should know this, but I've just had like a really busy week. That is 1/2. Sine 30 is cosine 60. I am a brilliant man. So that's 1/2 squared. So that's 1/4. Okay, so half makes it through this. 1/4 of the light that made it through the first polarizer makes it through the second polarizer. So we have a drop of 1/2, and then we have another reduction of 1/4. So 1/4 I1, or 1/8 I naught. So all things told, only about 16% of the light from this would come through there. Right? And if that didn't seem like a sensible number given these, realize that your eye does complicated biological stuff to these. Okay. So I'll show you guys a couple of demos that are more or less cool, but I'll let you guys think about this one in the meantime. Let's say that I went back to this scenario where I cancel all the light with two cross-polarized polarizers, and I put a third polarizer in the middle at a 45-degree angle. So I would encourage you to take a moment and stop and think about that and see if you get the right answer. So this is one of the things that's like very weird and non-intuitive.